Sushruta for NEET is now available on the Google Play Store. Try it out for free.
All right, so we discussed torque and then we discussed angular momentum. Now we are going to look, and then we introduced this concept called moment of inertia, right? So today we are going to look at how these ideas behave and how they, we discussed the parallelism with Newton's first and second law and the concepts around these things. So give me one more minute and then I will get going. So the fundamental equivalent of Newton's second law is the first line here, the last line here, dl by dt equals tau ext. Okay. Now, L is, you all know Newton's second law as dp by dt equals fext, right? Similarly, dl by dt equals tau ext means that the rate of change of angular momentum is equal to the impressed external torque. Okay. So now we then discussed the concept of angular momentum from 2 points of view. One is as the moment of the linear momentum, r cross mv, right? Now, the second definition for angular momentum was I times omega, right? I times omega is a direct equivalent of m times v. Okay. Now, omega is a vector, just as v is a vector, and I, right? Mass is a idea that is related to inertia. Like that, the moment of inertia is the rotational equivalent of mass. Okay. Integral r square dm represents the moment of inertia. Okay. So integral r square dm represents the moment of inertia, right? And therefore, the when we look at angular momentum L, we say that L is equal to I times omega, where omega is the angular velocity, right? So angular momentum equals the moment of inertia times the angular velocity, and therefore L and omega are typically in the same direction, right? We already explained omega as when something is rotating like this, omega is like that, right? So similarly, L also, when something is rotating like this, L also is like that. Okay. Now, if you want something to go rotate faster and faster and faster and faster, then you must apply torque also in the same direction as L and make it spin faster and faster and faster and faster. Okay. So, what is the most common way that torque is added, right? Now, in a merry-go-round, right, you have torque added, right? How does, if you are in a merry-go-round and it was a physically spinning merry-go-round, there will be a person who spins you, right? He will be, you are sitting at the one of the side roads, and there will be a person who is continuously spinning everybody, and it keeps going faster and faster and faster and faster, right? This is the physical merry-go-round, right? Now, if instead you had the what is called the torque-based answer, right? The torque-based answer comes from the center, okay? And how is torque imparted from the center? It is imparted through the use of a twisting force, okay? Now, this kind of twisting force is very important to understand because that is what most of the things that we see rotating in the world involve. For instance, the fan, right? The fan is rotating, right? And why is it rotating? It is when it rotates, what does the fan do? Right? It spreads air all over. Right? How does it spread air all over? It is driven by the blades brushing the air around it. Right? So the blades brush the air around it. Therefore, it is what drives the blades, right? There is a motor. More specifically, in the context of your home, there is an AC motor, right? A lot of children will have this little fan. When it's very hot, they will come to class and they will switch it on. There will be a battery inside. That is a DC motor. But again, in the context of mechanics, what is it doing? It is giving a twist, right? So this, in this case, the torque is given from the center. Okay, so so these are the two ideas here. Okay, now so what causes torque? Torque is caused by rate of change of total orbital angular momentum is equal to the sum of the external torques, and it is analogous to the rate of change of momentum is equal to the external force. So now we already discussed the figure skater, right? The figure skater, it is the Olympics are going on. You must be missing the ice skaters, but there are other types of people who are doing other kinds of things which involve some kind of rotation. Now, the figure skater, and there are figure skaters also in regular roller skating, you know. So in what does the figure skater do? The figure skater first uses her ability to generate rotational motion by using her body itself. Okay. Now, what is the external force that acts on the figure skater? It is essentially provided by the ground. Okay. Now, when you walk, what is the force? Like that, in this case, she applies a rotating force on herself and then starts to rotate, right? So if you push against the ground will push back against you. And if you spread your legs and then you produce a rotational, that is, one leg is going backwards, another leg is going forward, then that will produce rotation. Shall I show you? I have a rolling wheels in my chair, right? So like that. Okay. So you see, I'm rotating using the ability of myself to spin. Okay. All right. So now the figure skater, once she has started spinning, right? What she does is she starts to, she then stops applying any torque. Okay. So she's spinning fast around from the tip. She just stands on the tip and she's spinning fast. Okay. Then what does she do? She has to balance, apply enormous skill in balancing herself. Then what does she do? She moves her hands in. When she moves her hands in, what she is doing is she is reducing her moment of inertia. Okay. She is spinning with, initially her moment of inertia is I. She is spinning with rotational angular velocity omega naught. She pulls in her arms and such that her rotational inertia becomes 1/3, right? If you have strong arms, you can, when you pull it in, your rotational inertia will come down, right? And as a result, the rotational inertia becomes 1/3 of what it does. Why does it become 1/3? R square dm. If you have, let's say you hold some masses also in your hand, right? Then you have even more, if you have one weight in this hand, one weight in that hand, you have even more moment of inertia. When you pull it in, because it's R square dm, when you make R 0 and you're rotating about this axis, your moment of inertia is for the two heavy weights like your hands and the two weights, it becomes very little because your R is small. Okay, so now she starts to spin faster and faster and faster because there is conservation of angular momentum. Okay. Now, so what does conservation of angular momentum do? Because her moment of rotational inertia, reduces to 1/3, her speed, her new angular speed will triple. Okay, so that is how it works. Okay, so if you had a fan, right, which could also retract its blades, right, it will go very fast, but you won't get any air. Then otherwise, if you got going, right, then you put out the blades, right. Then if for some reason you felt that it has a lot of rust and it is not spinning a lot, then if you could retract the blades, it will help you, right? Then you can extend it when it's spinning and it reaches a good velocity. Okay, so these are all, I'm just giving you some tricks, but they don't usually work. Fans stay as, they don't change their moment of inertia like a figure skater. Okay, so a wheel of radius has rotation. So now, how does torque do work? Okay, so this is the second question that deals with torque doing work, right? Tau, right? Tau has the same dimensions as work itself. Okay, dl by dt equals tau, right? Tau is also, torque also has the same units as joule. Joule is a unit of work. Okay, now how does torque do work? If you spin it by a small angle theta, right? For each delta theta, it does work. F dot dx was work like that. Tau dot d theta will do work. Okay. Tau dot d theta will give you, remember, tau is a vector, d theta is also a vector. Tau dot d theta, the integral of tau dot d theta will do work. Okay. So when you integrate tau d theta, you will get the total work. Okay. Now, when you do dl by dt and L as I omega, right? So what happens is when you integrate you take the dt to the other side, right? Or you can write d omega by dt as d omega by d theta times d theta by dt. Okay, so you have I omega, right? D of I omega is I times d omega, right? So I times d omega by dt, right? dl by dt will become I times d omega by dt, assuming I is not changing, right? So I times d omega by dt can be written as d omega by d theta times d theta by dt. You all know that d theta by dt is again omega. So I omega d omega equals tau d theta. Okay, so integral I omega d omega will give you half I omega square, that is equal to integral tau d theta, which is the change in the kinetic energy. The work leads to a change in the kinetic energy, work energy theorem, right? So therefore, that's the idea behind half I omega square equals delta Ke. Please note this. Okay, so now a frictional force is applied tangentially to the wheel. You have a wheel of radius which has a rotational inertia. Now they give it a force. Frictional force is applied tangentially to bring it to stop. So it is already rotating. Slowly they are making it stop, right? So what causes it to stop? A frictional force. Maybe there is a boy who is putting his finger there. I don't know. Do not do such things. These are all dangerous. So, but somebody is applying a frictional force. That frictional force is producing a tau d theta. Okay, frictional force at a tangent is going to lead to r cross f, right? And it is applied over a period of time, right? So, what is the work done by the torque to stop the wheel? It is equal to its initial kinetic energy. That kinetic energy when of something which is spinning is half I omega square. Today we are also going to look at rolling, right? Rolling, what is the most common thing that rolls? It is the wheel, right? So here there is a wheel which is spinning without moving, right? So if it is spinning without moving, it is in the same place, it is rotating at 6.5 revolutions per second. What is omega? Omega is 2 pi by T. What is T? T is 1 by 6.5, right? Because it goes 6.5 revolutions in 1 second. What is the period for it? It is 1 by 6.5. So what is the omega 2 pi by T, right? 2 pi by 1 by 6.5 will give you the omega, okay? 2 pi by 1 by 6.5. 1 by 6.5, 6.5 will go to the numerator. Therefore, you have omega as 2 pi times 6.5, right? So, half I omega square will give you the change in the kinetic energy. Okay, so its initial energy is what? When you're rotating, it's half I omega square. Think of half I omega square also in this form. Okay, every particle, right, has a half mv square. V, you know, is r omega, right? So half mv square is the same as half m times r square times omega square. Okay, so mr square is omega. Okay, so I, in that sense, is a measure of that rotational ability. Okay? Integral r square dm, right? Therefore, keep that in mind. But then note that when you do I, right, you do an integral r square dm there. So keep that in mind. It's a tricky issue. But I wanted you to understand it using this. Okay. Now, there are what are called Kepler's laws in the context of planetary motion. Okay. Next class we will start planetary motion. We will do a very quick review of Kepler's laws, and Kepler's second law, right, deals with this idea called angular momentum. Okay. Kepler's first law states that the Earth and other planets go around the sun with the sun at one of its foci. So it go in an elliptical orbit, right? So he was the earliest person to discuss the heliocentric theory was Galileo, right? And after him came this person called Tycho Brahe. Tycho Brahe was a very rich man. He lived in Netherlands somewhere, and he was able to, because he was very rich, he could buy all the instruments to study all the planets in the sky. He then worked with this Kepler, and Johannes Kepler then created the three laws. The first law of Kepler states that the planets go around the sun in an elliptical orbit. Okay? Now, if you for several problems, if instead of elliptical you went to circular, you will still get reasonable answers. Okay, but elliptical is the correct answer. Elliptical and circular are not that different, but they are different. Okay, so now Kepler's second law states that the angle, the aerial velocity, so when it goes around, right, when it is close to the Earth, when it's close to the sun, right, it covers the angles faster. Okay, when it is further away, it covers the angle slower. Okay, so what he found was that the aerial velocity covered by the planet, dA by dt, with the sun at its focus, the aerial velocity was constant. So if you counted for maybe 1 month, right, the aerial velocity covered by the Earth and by Pluto. Pluto is the farthest of the planets. Okay. Now, the aerial velocity covered by Pluto and the Earth will be the same. What does that mean? Pluto will go only small distance because it's a very thin sector, right? It's a very thin sector, right? While the Earth will go a long distance in that same time frame. Okay, so what does that mean? dA by dt is a constant. Okay, now why is that so? It is so because the angular momentum of the planets are conserved, because there is no other external torque, right? The planets are continuously moving at a tangential way, right? While the force of attraction is perpendicular, right? Uniform circular motion also the same thing, right? But this is not uniform circular motion. This is elliptical motion. Even in elliptical motion, most often planets are moving in a tangential direction to the force. When that happens, there is what you end up with is this idea that there is, the force does not do work, right? We already discussed that, and also the torque that is there is no real torque that is produced by that motion. Okay, so as a result, what happens is angular momentum is conserved, I omega is conserved, and I omega is what? mr square omega. Okay, mr square omega is conserved. R square omega is the aerial velocity. Okay, you're moving in a circle, r square omega is the aerial velocity. I'll tell you why. Okay, what is the area of a circle? Pi r square, right? So that is what? What is pi? Pi is half the total angle, right? So half pi r square is the half 2 pi r square is the area. Okay, so in a short period of time, how much if something was moving in uniform circular motion, what will be the speed that it will be going through? In once it will be half r square theta. Okay, so half r square theta will be the angle covered, right? I'll tell you why. Think of the whole thing as a small triangle. Okay, this length is what? R theta. Okay, r times theta will give you the circumference. 2 pi r is what? Circumference, right? So r times 2 pi is what? The total angle, right? In radians. So r theta is the length of the arc that is subtended. So r theta times r times half. You think of this as a small triangle, right? Half times r theta will give you half base times height. Okay? So that will give you the area covered. So half r squared theta is the area of a small triangle. Okay? So now what is the corresponding area per second? dA by dt, it will be, and if you say r is constant, it will become 0.5 r square d theta by dt, and d theta by dt is omega. So half r square omega is the aerial velocity. Okay. So for this question, he is saying that the angular momentum of a planet is L and its mass is m, then its aerial velocity is what? It will be half r squared theta is going to be what, right? So half r square omega is going to be what? So L is equal to mr square omega. Therefore, half r square omega is going to be L divided by 2m, right? Because r cross mv, right? V is r omega, right? So based on that, L is equal to r cross mv. So and V is equal to r omega. Therefore, dA by dt is given by L by 2m. Okay. So understand the idea behind angular momentum, conservation of angular momentum in the context of planets. Okay, and I took maybe more time than I wanted to. I will not discuss this problem. If you want, we can discuss it privately or separately. But the equivalents we already discussed is translational equilibrium and rotational equilibrium. Right now, then we also discussed some of these ideas last class. The conservation of angular momentum when there is no external torque, L is a constant, We already discussed the problem with that. Then we also discussed this idea with respect to constant velocity. Then, then we went on to discuss moment of a force, right? Moment of a force is the torque, right? And therefore we introduced the couple, right? And after we introduce the couple, we introduce the lever. And after we introduce the lever, we introduce center of gravity, and then we introduce the seesaw, right? Or the case of a lever with multiple supports, right? And then we explained how one can apply moments, right? So in this case, let me go over this illustration one more time because it is very important to understand how to apply moments. Okay? So now this AB is a rod whose weight is 4g. Okay, its weight is 4g, so mass is 4 times g is weight. Now there is a force at a point P which is equal to W1, and that force is 6g. Okay, now the rod itself is so think of it like this: there is a person sitting on a bench, right? The bench has two stilts here, right? Each of the stilts is applying a angle force on the bench, right? So those two forces are K1 and K2. Okay, so he's sitting like this on a bench with two stilts, right? Maybe in a park. I'm sure you've seen a park bench with two stilts, right? So, so he is sitting not exactly in the middle. He is sitting somewhere in the side, right? So when he is sitting in the side, it still doesn't fall. Why does it not fall? So there are two forces, R1 and R2, which are unequal. Okay. Now, what is the value of the forces? It's at rest. He doesn't fall. Nobody falls. Everything is stationary. Therefore, the R1 plus R2 equals W1 plus W. Right. So that is the force equation in the vertical direction. Right. But is that enough to solve the problem? No. You need one more equation. And that equation comes by applying moments. Because it is also not rotating, the net external torque is 0, and he is looking at taking moments about this point, G, right? So he has R cross F for PG times W1, right? And this one is R2 times K2G and R1 times K1G, right? So negative R1 times K1G plus R2 times K2G plus W1 times PG, right? So you must, of course, take care of the direction. W1 times PG is this way. R2 times R2 times K2G is also this way, but the third one is into the paper, right? It is R1 times K1G is into the paper. These two are out towards you. The third one is into the paper, right? So then you have the equation. Total moments is 0. So you sum all the torques, the three torques. So what is torque? R cross F, right? So you sum these three torques and equate it to 0. So now you have two equations. There are two unknowns. You can solve for R1 and R2. Okay. Similarly, we also discussed the ladder problem. The ladder problem is often asked in NEET and JEE. This ladder problem is a little different from the standard ladder problem. The standard ladder problem involves two frictions. There is one friction here and there's another friction there. Okay. Now, how does friction work? That's very important. See, the ladder is about to slip this way. Therefore, friction will be this way. In this case, the ladder is about to slip this way. Therefore, friction will be this way. Okay. So, but this wall is smooth, right? So, even then, if there has to be at least one form of friction, otherwise it will slip. Okay. So, one of the two frictions, one of the surfaces has to be rough for there to be for it to stay where the ladder to stay where it is. Okay. And so you end up with three sets of equations: two force equations, force in the horizontal direction, force in the vertical direction, and one set of moments. Most often people take moments about the point B. Do you know why? because you eliminate two forces. One is the friction and the other is N1, because the R cross F on these two forces will be 0. Okay, so you just then have only 1, 2, and in some cases 3. Okay, now what is very tricky in these problems is one of the forces will remember that F1 and F2. If there was an F1 and an F2, remember that F1 and F2 you are both unknowns. Okay, so it is very tricky because of that. Okay, so the F1 and F2 along with N1 and N2, so you have 4 unknowns and you don't have 4 equations, you have only 3 equations. So they will always ask you when it is just about to slip. Okay, when it's just about to slip either at the bottom or at the top. Okay, so you must understand these questions, they are not that easy because you have to apply both moments and force equations. Ladder problems most often involve both. Okay, so in this case, the wall is smooth, right? So that changes everything. If the wall is not smooth, right, then you end up with 2 mu's. So you have mu1 and mu2, and you have 2 equations. Okay, so then you will end up with multiple unknowns, and they will tell you it is about to slip, and therefore that means that the frictional force is mu times n. Okay, so keep that in mind when you look at these ladder problems. Okay, so then we discussed moment of inertia. We already discussed half I omega square, right? And that gave us an idea also as to how you what is the kinetic energy is half I omega square. The angular momentum is I omega. Okay, so remember those two. And the important idea here is how do you calculate the moment of inertia. Moment of inertia, as I explained, is given by sigma MIRI square. And when you have that kind of a sigma, you end up doing an integral, right? And so most often you do, like when we did center of mass, we did integral R dm by m. Here we do R square dm, and there is no by m in the denominator because I is itself a quantity like mass. So integral R square dm gives you the moment of inertia of a continuous body. Okay, so now if it is not a continuous body, if it's a discrete body, then you do sigma mi R square. So now if you had just a circular ring and you are spinning it about this axis, right, all the r's are constant, so you take the r's out, so it just becomes R square times dm integral dm, right? Integral dm is m, right? Therefore it is just mr square. If you have a circular ring, right? So if you have a cylinder, it is mr square, also mr square. If you have a hollow cylinder with a radius r, very thin hollow cylinder with a radius r, it is mr square. If it had a thickness, then you have to do the corresponding integration. So and so if you had a full disk, right? If you had a disk, it becomes half r square when you do the integration, right? So thin circular ring mr square. This is a 3-particle system. Now let's go to the other one. Uniform circular disk is mr square by 2. I discussed this integration last time, right? 2 pi r, you take a thin disk, its moment of inertia we already did, right? You can then integrate those moments of inertia. Otherwise, so it is r square times dm, right? So going from 0 to r, then you can still end up with the correct answer. But most often how people do is they take a thin disk, 2 pi r dr rho, right? Rho is the mass per unit area, right? Rho times 2 pi r dr will give you m times, it is all those particles in that thin disk are at a distance r square. Therefore di equals 2 pi r dr rho times r square, so you end up with r cubed by 3. So r to the power of 4 by 4, because it's r cubed dr integration from 0 to r, so r to the power of 4 by 4. But there is a extra 2 here, therefore that 2 and the 4 will cancel and you will have just a half in the denominator, right? And you know pi r square times rho, pi r square is the area. Area times rho is gives you the total mass, right? So so from that, that is how you do the uniform disk. The rod about so the rod about its center is ml square by 12. Remember that the moment of inertia about the center of mass is always the lowest. So how do you do that? So you take anything, so between 0 to L by 2, right, times 2, right, 0 to L by 2, integral L dl, right, L or L square dl, like r square dm, so L square dl, right? So L square dl from 0 to L by 2, right? L square dl will become L cubed by 3, right? So L cubed by 3 will eventually fall out, and therefore you will have from 0 to L by 2, you will have 1 by L cubed by 3 times 1 by 8, right? But then there will be the multiplied by the 2, right? So the 2 and the 8 will cancel, and you will end up with just a 4, right? So in the denominator, you will end up with 3 times 4. So ml square by 12. Okay. So L square dl integral will come here. Now, the what about if you had to do it about this point? That's even simpler. Then that will be much more. It will be ml square by 3 because it's L square dl 0 to L, right? So that will be L square by 3. There is no by 2 there, right? So, and it is the integral goes 0 to L, right? So it will become L square dl. So it will become L cubed by 3, right? So now let's look at this problem. Okay, a horizontal circular platform of radius 0.5 meters. Okay, so what is the radius of that circular platform? 0.5 meters. What is the mass? 0.5 kgs. So tell me the moment of inertia, circular disk, moment of inertia, mr square by 2, right? So that is what? 0.5 square times 0.45 by 2. Okay, two massless spring toy guns, two massless spring toy gun 1, toy gun 2, each carry a steel ball of mass 0.5 and attach the platform on either side, right? Each gun fires simultaneously, so it imparts a MV, right? So when you fire the gun, what happens to you? What happens to this, right? You shoot, you will have a recoil, right? That recoil is going to make it. So if you shoot this way, right? You shoot this way, it is going to start spinning this way. Okay. If you shoot this way, that is also going to cause it to spin that way. Okay. So because they form a couple, right? And they shoot this way, right? The recoil is going to make it spin this way. Okay. So they are both in the same direction. R cross S. If not this way, the recoil is this way, right? So R cross S, right, is going to be up. R cross S is also going to be up. So both of them will be upwards. Okay. So between the same direction, therefore it will be additive. If they were both shooting this way, right, then the recoils will cancel out. Okay. It will not cause rotation. It will tend to push the whole platform down. In this case, there is no net impulse caused by it, right? So it will tend to make it rotate. Okay. So the recoils will make it rotate, right? If it was both fired like this, there will be no torque because the two torques will cancel out. R cross F will due to this will be like this. R cross F will due to this will be like that, right? So up and down will cancel if they are both in the same direction. Because they are in opposite directions, it produces that twisting motion. Okay. So now R cross mv1 plus R cross mv2 will equal I omega. So he's asking you to calculate omega, right? So what was the basis of all this? Basis of all this was to help you understand how this works, right? I made a mistake here. Nobody saw it, right? It is half m r square, 0.45. Okay, so 0.25 times this is r cross mv, right? So it's at this distance is 0.25, so that is r, right? M is each of the bullets is 0.05, right? The velocity with which it is fired is 9, right? So 0.25 times 0.05 times 9 times 2, because there are two guns, okay, equals half uh, uh, equals half mr square times omega. This is a conservation of angular momentum problem. Okay. So uniform cylinder we already discussed. Hollow cylinder is mr square. If it is a non-hollow solid cylinder, it is mr square by 2, because the cylinder is just a series of rings. The ring is mr square by 2, right? So so a cylinder is just about the same axis is just a series of rings. Okay. So and those are just additive. You can just break it into a series of rings and it will be additive. So it is also mr square by 2. You solve a lot of these moment of inertia problems, so that if you have any issues with moment of inertia, you can easily catch it. You can easily solve the problem. Now here he is doing this sphere. Okay, moment of inertia of a sphere. Okay, now a sphere. How do you do the moment of inertia of a sphere? You break it up into many hollow surfaces, spherical surfaces. Now, what is the area of a spherical surface? 4 pi r square, right? So now you take the whole sphere. What is its volume? 4 by 3 pi r cube, right? So now m by 4 by 3 pi r cube will give you your rho. Okay, rho is equal to m by 4 by 3 pi r cube. Okay. Now, if you take a hollow sphere, its area is 4 pi r square. 4 pi r square, let's say its thickness is a very thin thickness of dr. So 4 pi r square dr times r square, 4 pi r square dr is dm times rho. 4 pi r square dr times rho is dm. So dm times r square dm. So this is dm, this is r square. So when you do r square dm, you have one r square here, another r square here. R to the power of 4 dr will become r to the power of 5 by 5. Okay, so that is how you end up with this 5. Then eventually you then remove 4 by 3 pi r squared from this. Okay, so you divide and multiply by 3, you will have 4 by 3 pi r cube. That 4 by 3 pi r cube rho will become m. So it will become n r squared times, and then the 3, because you multiplied, you'll also have to divide by 3, right? So 3 times 4 by 3 pi r cubed times r square. Okay, so you end up with 3mr square by 5. Okay, so I derived this also because this is how you solve these moment of inertia problems. For a cylinder also you can use this thing, but a cylinder is just a set of stacked what do you call discs, right? Set of stacked solid discs, uniform discs. Okay, therefore it is also mr square by 2. Now we introduce this idea called radius of gyration, right? If I is equal to mk square, k is said to be the radius of gyration. Now, if you had something which is 3 by 5 mr square, 3r square by 5 is equal to k square. Okay, k is the radius of gyration, right? So root 3 by root 5 times r is k for a sphere. Okay, radius of gyration is that quantity which makes it a perfect mk square. Okay, so remember that. Then we introduce these two theorems. The perpendicular axis. First, let's look at the parallel axis theorem, simpler one, right? We already told you that for any body, the moment of inertia about the center of mass will be the lowest about any parallel axis. See, when you want to make this spin like this versus making it spin like this, right? There's a huge difference. The moment of inertia when you make it spin like this is ml square by 3. When you make it spin like this, the moment of inertia is ml square by 12. Much less. Okay, so but when you make it spin like this, it is much more. Although it is the same body, the mass is the same. Okay? So it takes more effort to make it spin like this, right? So the corresponding half I omega square is much more. Okay, so so the parallel axis theorem says that ml square by 12 plus this distance is what? L by 2, right? Plus m times L by 2 square. Notice the A here. Notice this term. ICM plus MA square will give you I about a different axis. Okay, so I about this is ml square by 12 plus m times A is what? L by 2, right? So m times L square by 4, right? So ml square by 12 plus ml square by 4 happens to also be ml square by 3. That is another way to calculate the whole rod versus the rod about the center of mass. Okay, so ICM plus MA square equals IZ prime. Okay, so that is how one can evaluate that. Now, the other rule is this perpendicular axis theorem. Okay, so now if you had to make this rod spin like this versus this rod spin like this, right? Now that is what this perpendicular axis theorem states, right? So when you make something, when you make a, let's say you had a disc like this and it was spinning like this, right? The disc was spinning like this, like if you made a, your dosa plate spin, which I don't know why you do that, but so that kind of a spinning the moment of inertia is half ma square, right? Now instead, if you made it spin like this, instead of making it spin this way, right? You have a disc, circular disc. Instead of making it spin like that, you make the disc itself spin like this, right? So how do you do that? How do you calculate that? The moment of inertia Iz equals Ix plus Iy. Therefore, Iz will equal Ix plus Iy. Okay, so remember that. Ix and Iy in the case of the circular disc will be, because it's symmetrical, will be the same. So Iz will equal 2 times Ix. So if you had to make a disc and you had to spin it about a diameter, this is how you will solve that using the perpendicular axis theorem. Iz equals Ix plus Iy. All right. So the moment of inertia of a uniform cylinder of length, I think we discussed this, but let me go over. Now here he is asking if you could make a uniform cylinder, right? When will it? So the volume is fixed. Okay. Now when will its moment of inertia be the minimum? When you make it longer, or when you make it longer and thinner, or when you make it shorter and fatter, right? Actually, there is a judicious mix where it becomes the best. Okay, it is in somewhere in between is the answer. And when is it minimum? It becomes a maximum minimum problem. I is equal to m times L square by 12 plus R square by 4. Okay, so because he's not making it spin like this, when you make it spin like this, we already discussed, right? It is mr square by 2, right? So now it has a fixed length too, right? So now instead of making it spin like this, he's making it spin like this. Moment of inertia of uniform cylinder about its perpendicular bisector. So if you assume this is the cylinder, right? It's like this has some radius. Now he's making it spin like this. Okay. And now he's asking, when is it easiest to make it spin like that? Okay. So the moment of inertia here is ml square by 2 plus r square by 4. Okay. So that is the moment of inertia, and therefore the volume is pi r square times L. So now you, because V is a constant, you can write this all in terms of an equation, just one variable, right? Now, whether that variable is R or whether the variable is L is up to you. Okay, so you can write this, you can write R square as V by pi L, right? When you write R square as V by pi L, you then have an equation only in L. Then you differentiate that di by dl equals 0, will give you the point where it becomes minimum, and then will get one of the answers there. All right. So that is with respect to these moment of inertia questions. The final idea that we are going to deal with is called rolling friction. Now, why do things roll, right? Sunil Gavaskar, right? He once said that in Shivaji Park, right, where he played a lot of his cricket, where a lot of other people played cricket, if you hit a straight drive, and you got the cricket ball rolling, he said it will go all the way, because rolling friction is much less than sliding friction. That was the point there. Okay, when something is rolling, right, it just touches the ground a little bit, tuck, 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 maybe it, and if there is no resistance, the minimal resistance, it will just roll all the way. Of course, in grass, if there is a lot of grass, the grass will add to the rolling friction, right? But otherwise, rolling friction is very minimal. Okay. Now, the force resisting the motion when a body rolls on the surface, it is mainly caused by non-elastic effects. Okay. So now, when a ball rolls or a body rolls, right, it has two kinds of kinetic energy. One is from the rolling, and the other is from the translation. It has both translational and rotational motion. The rotational kinetic energy is half I omega square, right? The translational kinetic energy is half mv square, right? Now, V and omega are related. V is equal to R omega, right? So you have 1 by 2 I omega square plus half mv square, and V is equal to R omega, right? So if you know ICM, which is the and it is rotating about its center of mass, then you will end up with an equation similar to this one. This one, half times ICM plus mr square omega square, because V is equal to R omega. Okay, so the angular momentum of the body is also changing, right? And we know that when a body is rotating and translating, there's an angular momentum seen from the center of mass frame and the angular momentum as it translates. The angular momentum from the center of mass frame is the I omega piece. Then there is also the R cross mv piece. Okay, so you end up with two components for the angular momentum. Total angular momentum is got from the instantaneous rolling velocity, noting that it is translating a velocity v and has a radius r. The R omega is the velocity. Okay. So now, rolling and sliding friction are a little different. Okay. Sliding friction, you already know, mu times n, right? N is the normal force, mu times n will give you sliding friction. Body rolls, there's a friction which does work in slowing the body and causing its angular velocity to decline. Okay. So it is a torque producing friction, but it is much less. Okay. So now when a sphere is rolling without slipping, right, there is, like, look at the points. See this point A, right? The this point is going backwards. This point C is going forwards, okay? And this point is somewhere in between, okay? So this point is translating, okay? This point is going backwards, this point is going forwards, but the important point is that when point B is moving with a velocity V, this point is moving with twice that velocity, and this in the forward direction. This point is moving with twice the velocity in the reverse direction. Okay, so VC minus VB will equal VB minus VA. Okay, so what you need to make sure is VC minus VA modulus will equal 4 times VB. Okay, if VB is moving at velocity V, if it is rotating like this, right, VC will be moving at twice that velocity in this direction, and VA will be moving at twice the velocity in the opposite direction. Okay, so this is a very simple idea, but it's a easy marks for you. Now, now what he is doing is he's asking you to keep that thought in mind as we look at this. Okay, this shows a system consisting of a ring of outer radius rolling clockwise. The important word here is rolling without slipping. Now, what is slipping while rolling, right? See, normally when you roll, you might roll like this. Perfect rolling, right? So that is rolling without slipping. But sometimes, like when you see these braking cars, right? Right? Then for some period, they will roll and also slip. Okay, so that is as an important idea. So I will look at it. My 1 hour is over. So I'm going to look at this idea very quickly next time before we move on to the next topic in for class 11. Okay, so till then, what I'm going to advocate for all the students is, before I come back and look at more rolling problems, etc., is I am going to ask you all to spend a little time understanding moment of inertia and rolling a little more before we proceed a little bit further. I will spend maybe half a class or one more class explaining rolling, and then we will move on to very quickly to the next topic for class. So try to understand moment of inertia, try to understand a little bit of rolling as well, but of course, most importantly, understand angular momentum and torque. Okay, there are a lot of problems which can come in angular momentum and torque. Of course, there's the ladder set of problems, there is the rolling set of problems, there is the I omega problems, there is the d omega by dt alpha angular acceleration related problems, and of course there is the planetary problems, right? Many different types of problems. Then there's the kinetic energy problems, rolling kinetic energy related problems, right? So the variety of the problems is, and the material also is a little bit hard, but the variety of the problems they ask in the context of rolling is much more. That's why you have to spend a little more effort, do a lot more different types of problems in the case of rolling, in the case of rotation, and then that will prepare you better for rotation. So please spend quite some time solving problems, and we will do some more problems which deal with rolling next class. I have a couple, and then we will go from there on to look at additional details dealing with these ideas. Okay, so I have a few more problems also, but I have a little bit run out of time. But I will look at these problems next class. So until then, my advice to all students is to spend your time trying to solve as many problems as you can. All right. Okay. I will see you again next class.